Okay, thank you. So what I'm going to talk about is really work that was done a long time ago, and that's maybe a long time ago in everybody's sense rather than just Leslie. But at the time it seemed to fall on completely deaf ears. Maybe it still will, I don't know, but let's give it a try. So I should point out that this is joint work with Magnus Bordewich, who isn't here, and Marek Karpinski, who is. So the main thrust will be about counting independent sets in hypergraphs, so I'll talk about some other stuff maybe if I have time. So VE will be a hypergraph H. The maximum degree is delta. So the minimum edge size we'll take as being M. Now a lot of the people who've been working in this area seem to use K for this, but M is now K. So for each edge in the hypergraph, it's a subset of the vertex set, and we're assuming that the cardinality of these sets is always at least M. The maximum degree is the maximum number of edges in which any vertex falls. I should say that because there are other definitions of degree in hypergraphs, but this is perhaps the most common. An independent set is a set in which no edge is a subset of that. So there's no edge in E which is a subset of I, if I is an independent set, and we'll let omega be the set of all independent sets in H. So here is an independent set. So these are the edges. If you look, you can see that none of them is full. But if I were to add that one, this is not an independent set because this is full. Again, there are many other definitions of independent set in hypergraph, but this is the one that will be used throughout. So we could consider a simple Markov chain on this setup, which is the Glauber dynamics, it's usually called. So the state space is the set of all independent sets, and starting from some independent set, a transition is given by picking a vertex in the hypergraph uniformly at random. With probability of half, we augment IT with V. Delete IT from V. Of course, it may not be in there, in which case this does nothing. With probability of half, we set V, we add V to IT. So IT prime T. So if I prime T is indeed an independent set, which of course it may not be, then IT plus 1 will be I prime T. Otherwise, we do nothing and continue. So it's fairly clear that this is irreducible because we could go from any independent set to any other independent set, say through the empty independent set. It's aperiodic. Well, that's fairly easy to see because there are a lot of moves that do nothing. And it's symmetric because we do both these things with probability of half. So the stationary distribution is uniform on omega. That is the probability that we're in any independent set after long enough is about 1 over the size of the set omega. So the question is, of course, so pi I I'll use to mean the steady state distribution, even though here it'll always be just 1 over omega. So how big do we need to make T to get close enough to uniform? Well, one approach to bounding convergence time is to use coupling. So coupling is a random process on omega cross omega such that marginally both IT and JD are faithful copies of M. And we usually measure convergence in this setting by total variation distance, which is sort of half the L1 norm of the difference between the distribution we have at time t and the equilibrium distribution pi. So if we can design the coupling so that IT and JT quickly become close, then we have this very old lemma which says that if JT was to start in the stationary distribution, then the variation distance is at most the probability that IT is not equal to JT. So of course, we don't know what the stationary, well, we can't sample from the stationary distribution, so JT is a kind of notional copy of the process, whereas IT is the one that we're actually interested in. Okay? So path coupling is a way of trying to make coupling a bit easier. And when it's applicable, it gives a simple way to devise a suitable coupling. So we take any metric on omega, and suppose S is a subset of omega cross omega such that for all ij in omega cross omega, there is a path of transitions from I to j. I think that should be S cross S, but no, that should be S, sorry. There's a path of transitions from I to j for which each of these is in S, and, oh no, maybe it's okay because it's implied by this. So the distance is the distance between successive ones. So this is a path along which the distances are kind of preserved by the steps. And then we need only define the coupling for pairs in S. And we extend the coupling to any pair via shortest path in S. So this will become a shortest path. So the theorem that drives this is from a paper with Russ Bowley in 1997, that if we can show that for all pairs in S, the expected distance goes down in one step, there's some beta less than 1, such that the expected distance at the next step is less than or equal to beta times the distance at this step, then the mixing time, which is the time taken for the variation distance to become less than epsilon, is this. So it's log d over epsilon over 1 minus beta, where d is the maximum distance between any pair of states in this metric. So if we can make a suitable choice of S and D, it greatly simplifies both the definition and the analysis of a coupling. So I'll take a stupid example, but it's one that shows how the method works, which is independent sets in graphs. So this is a case m equals 2 of the hypergraph independent set problem, and we'll just take d to be Hamming distance. So it's the number of vertices in which the two copies will differ. And S will just be the set of pairs at distance 1. And we'll use the identity coupling, that is, we just perform the same move in both chains. So suppose IT is JT with W removed. By symmetry, that's enough. So which transitions change the distance? So if M picks a neighbour of W and tries to insert itself, it could be rejected in JT but accepted in IT. That is, if no other neighbour of V is occupied, which we have to assume is the worst case. So this is the bad thing that can happen. But the good thing is that we might actually pick W, in which case it can be accepted in both chains. So if we do the analysis of how the distance changes, it started out as 1. If we chose W, it was decreased by 1 over n. But if we chose some neighbour of W, which we would do with probability delta over n, then the distance would increase by a half. A half because we only did the thing with probability a half. So that's a simple path coupling analysis. So what do we get? So we've got the expected distance is the distance it started from, which was 1 times this factor. So this beta is 2n plus delta minus 2 over 2n. So this thing really only works if delta is strictly less than 2, okay? Which is not really an astounding result. But if delta was less than 2, then you've got this mixing time, right? So you'd be in good shape. So obviously this doesn't yield anything of interest, but there are various ways we can go with this idea. I mean, you can change the chain, you can change the metric, or you can change the coupling, and all of those sometimes give you something better. So if we tune this up a bit better, then we can get delta less than or equal to 4. And that was first done by Luby and Vigoda in 1999 using a kind of bare hands coupling argument, and then using this argument by myself and Catherine Greenhill in 2000. So this gives an F-pras for counting independent sets in graphs. On the other hand, with Alan Fries and Mark Jerram, we showed that there is no F-pras when delta's at least 25. So there's been a lot of stuff done on independent sets in graphs, much of which we've heard about here. Whites gave a polynomial time algorithm for approximately counting independent sets in graphs when delta is less than or equal to 5, using an entirely different approach. I was surprised to find out that nobody actually knows what the exponent of this algorithm is. He says it's polynomial time, and you could deduce it from what's in the paper, but nobody is willing to give me a guess of what those question marks should be. I think certainly it's more than 2, but how much more than 2, I don't know. So what this does, it uses a tree representation. We've heard a little bit about this here already. And the depth of the tree is bounded because you have this correlation decay in the system. So this algorithm was a major achievement because it matched the conjecture, which was given in the paper with Alan Fries and Mark Jerram, that the answer was that you could only do up to 5, and then 6 was going to be difficult. But the other remarkable thing about this was that it's deterministic. So everything up to here had been randomized. And in fact, there was a belief growing that you had to have randomization to do this. Certainly if the problem started out as a number p complete exact counting problem. But on the other side, Alan Sly dramatically improved the construction that I'd had with Mark and Alan, and showed that there's no F-pras when delta's at least 6, so closing the bound on the other side. And these results have been generalized to what are called two-spin systems, which we've heard a bit about. But they don't seem to generalize so easily to hypergraphs and or more than 2 spins. So these results produce this feeling that that this kind of Markov chain approach was the wrong way to go, and that the right way was to use correlation decay. But that doesn't really seem to be true, as we'll see. So, suppose we use path coupling on hypergraphs. Then if using the identity coupling, the same analysis applies. Then we take the same kind of coupling. So here we've got the one that's different, and there are delta edges surrounding it. And there's delta vertices that might be inserted into JT but not into IT. So we would still end up requiring delta less than or equal to 2. I say less than or equal to because the equality case is actually still good for us. But so how might we do better? So if we look at what the bad configuration is, it's this, right? So we've got delta edges that are almost full, and we think we might add one of these next, in which case it would go wrong and we'd increase the distance. So there are delta bad vertices. In one step, we're obviously more likely to hit one of those than we are to hit W. So these are the bad vertices. There's 3 times as much chance of hitting one of those as hitting this. But if we look at this, we're far more likely to hit one of these guys, right? And if we do, then things actually get better for us. So we might hit that one, then we might hit that one, and that one, and that one. Now we hit this guy that started out being bad, and he doesn't do us any harm, right? So what we see is that there are bad configurations. We don't expect any immediate contraction in distance, but it's likely that we'll move to a better configuration before the distance changes. So we first tried to use this argument with what was called stopping times. So what we did was to just run the process and try and look what happened until, we got the bad event that the distance increased. So this was originally used by myself, Catherine Greenhill, Leslie Glauber, Mark Jerram and Mike Mitzenmacher in 2001, and we obtained some small improvement for the graph colouring Markov chain. But there have been later improvements to this method by Hayes and Vigoda, and paper with Magnus Bordwich and Marek Karpitsky. So so how could we modify the metric? So we could penalize the bad configurations in the metric so that movement towards better configurations now results in contraction. So knocking out those vertices is actually going to be doing us some good rather than just doing nothing. So we have to balance this, of course, with weaker contraction on the good configurations, which have some probability of becoming bad. And, of course, we get an increase in the maximum distance between any pair of states. I won't dwell too much on these things, but so the intuition is that each pair of states that are one apart has some contraction, which is the expected value of the next distance divided by the distance now. And so we identify the critical configurations, which have got expected contraction at alpha 0, and we increase the distance for those so that their expected contraction reduces, but the expected contraction of their neighbours increases. And we stop when these balance. This will give us some newer set of critical configurations, and we just repeat for those, okay? So what are the bad configurations? Well, we said before, if we take IT and JT at distance 1, with IT as JT plus W, then the bad set of edges are these things, where E has I occupied vertices, will define this set EI, and the bad configuration is that the set of of edges with n minus 2 occupied vertices is delta. Of course, there's this guy which we're kind of ignoring. So if there's only one that's not occupied, this is bad. So how bad is the configuration? Its badness increases with the number of occupied vertices. So suppose edge EI, an edge in EI, it's got I occupied vertices, has badness CI. And the CI will be a non-decreasing set of constants. And we'll assume that each edge containing W contributes independently to the badness of the configuration, by which I mean we'll just add up. So our new metric will be the sum from I equals 0 up to n minus 2 of CI times EI. And without loss of generality, we'll assume that the last one is 1. It doesn't really matter what we chose it to be, but it would all come out in the wash. But 1 seems the most sensible choice. And for convenience, we'll suppose that C minus 1 is the same as C naught, and Cm minus 1 is delta plus 1. So what can happen? If W is chosen, then the distance decreases by this, okay? Because the two things are now the same. So the contribution to the expected change is minus that times the probability that we chose it, which is basically 1 over n, which I've, for some reason, best known to myself, written as 2 over 2n. But if we insert a vertex, then we increase the distance by Ci plus 1 minus Ci for each edge in EI that contains V. So, and this holds for I is n minus 2, since we chose Cm minus 1 to be this. So the contribution of all the insertions is 1 over 2m, because we only did it with probability of half, times the increase, times the maximum number of edges that could have affected. If we delete a vertex, then we decrease the distance by the same amount for each of these edges, and this holds also for I equals 0 by the choice of C minus 1. So the contribution for all the deletions is this. So we get an I here rather than M that we had there before. So this is going to actually decrease the distance. So what is the actual expected change in distance? It's this complicated thing here. So it's, if I multiply through by 2n, it's minus 2 times the good case, if you like, plus this from what would seem to be the bad cases. But we also get this. So some of the bad things have now become good, and this is the case where we didn't hit anything that was at all dangerous, which we saw in the example. So if you work this out, it comes to this. And what we want is the expected value of dt plus 1 minus dt is less than or equal to minus gamma for all configurations, but in some positive gamma. So what we want a solution to is this, which is the right-hand side of what we saw before, subject to these being non-decreasing, and the constraints that we put on them there. So this gives us a set of linear inequalities. We can check the conditions on this and find out for which m and delta we have delta greater than gamma greater than 0. So you can see that effectively we need to solve a linear program to optimize gamma subject to these inequalities. So in the first workshop, Chris Moore presented a similar kind of application of path coupling to moving around hard disks in the plane, where he again produced a linear program which he had to optimize to design the best metric. So it seems to be quite closely related to this. So what is the optimal solution to that linear program? So it turns out to be this rather horrible quantity, but the important thing is this got this m minus delta minus 2. And you can see fairly easily that this is positive for m greater or equal to delta plus 2. It needs m at least 5, but that's not really of too much importance here. I mean, we're talking about relatively large edge size. So we have contraction and therefore rapid mixing of m in big O n log n time whenever m is at least the max of delta plus 2 and 5. So it might be possible to improve this. I say we didn't at the time because nobody seemed to be interested, so we just left it there and moved on. So in the meantime, though, there's been some other work on this. So you look at what other work was done. In the Dyer and Greenhill paper on independent sets and graphs, it actually shows rapid mixing for hypergraphs with m equals 3 and delta equals 3. Now, you might think that should be m at least 3 and delta equals 3, but it isn't, in fact, if you look at the paper. It is exactly that, right? That was the case we could do. And the first attempt we had at this, the stopping time, gave rapid mixing only for m greater or equal to 2 delta plus 1. But we also showed that there is no f-pras if delta is at least 694 times 2 to the m plus 1 over 2. So this is something times 2 to the m over 2, okay? So that's in that paper. More recently, Liu and Lu gave an FP-TAS, that's using the correlation decay method, for all m at least 2 and delta less than or equal to 5. So this is really like White's result, basically. Even more recently, these people, Bezakova, Galanis, Goldberg, Groh, and Stefankovic, have shown that there is an FP-TAS for m at least 3 and delta equals 6, also using correlation decay. And that's a very tight result. That seems to be optimal. But they also show that there is an FP-TAS for m at least 1.66 delta using correlation decay. Now you can see that this is actually worse than the result you've just seen, okay? So correlation decay is not the magic bullet for slaying all these kind of problems, unfortunately. So they also improved the hardness to 20, 2 to the m over 2, which is, you can see, quite a lot less than this. But very recently, at this meeting, Herman and Zhang have announced an f-pras when delta is less than or equal to some constant whose value I don't know, times 2 to the m over 2 over m squared. So this is seems quite a good result because it sort of matches these upper bounds to some extent, and in fact this proves something that we had thought about this problem, which was that it was sort of m equals delta was kind of or close to delta was where things went wrong. So this is a very long way from this so-called diagonal. But But notice that this doesn't completely settle the problem. I mean, this is a long way from doing that, because even if this c is 1, 2 to the m over 2 over m squared is only better than m plus 2 if m is at least 30, right? So it doesn't cover any of the small cases, but nonetheless, it's a very interesting result, and we hope to hear something about it this week. As I understand it, the technique is more related to the Markov chain approach than it is to the correlation decay, but I don't know completely what it's about. So, okay, so just to spend the last 10 minutes or so. So we did look at some other problems, and we looked at colouring hypergraphs, Q colouring. So the history of this is that for m equals 2, graphs, rapid mixing for Q at least 2 delta was shown long ago by Mark Jerram in 1994, using this kind of bare hands coupling, and it was improved to Q bigger than 11 delta over 6 using a complicated path coupling by Eric Vagoda in 2000. And for general graphs, this is still the best thing that's known. After 16 years, nobody's improved this result. There are better things known if you assume something about the structure of the graph, right, like the girth in particular. But in general, this is the best that's known. So we looked at this, and it turns out that if m is at least 4, it's trivial to get Q bigger than delta. So this seems to be very easy, and probably it should be improved from there, but we didn't. We stopped because it seemed such an easy result, and we couldn't see what we could do at the time to improve it. So the only case that was left was m equals 3. So using the method here, we could show that hypergraph colouring mixes rapidly if Q is at least 3 over 2 delta plus 1. And this improved an argument that was in the previous paper, which was 1.65 delta, and required that delta be quite large. So how does correlation decay manage with this? Well, not really very well. So Garmanik and Katz gave a FP-TAS, in fact, for list colouring, when Q is at least 2.843 delta. And it was improved for graph colouring by Liu and Yin in 2013, who gave 2.581 delta. But notice that both of these are worse than Jerram's result in 1994. So it seems that correlation decay is not necessarily the right way to go if you go away from two-spin systems on graphs. I'll just sketch, since I have a few minutes left, how this was done for m equals 3. So we identify 4 classes which are defined like this. So we've got 2 copies that differ in one vertex, and we'll say the 2 colours are R and B, and the other colour would say be G, green. And these are the dangerous sets, if you like, in decreasing order. And this is what happens if we immediately going to get something going wrong. So it's where the R's and B's are that things are going to go wrong. G, we can just do what we like. So we get these 4 sets, and we use the same idea of defining a metric which depends on the size of these sets and use the same kind of thing. And this time we get a similar kind of, perhaps even more horrible expression, which this is the original good case. These contain a mixture of good and bad, and that's what happens for E1, that's what happens for E2, E3, E4. And if we set C1 equals 1, we get these values for C2, C3, and C4. And this gives us that the expected value decreases whenever we have this gamma less than 1, essentially, I suppose. So this is the... So if we work out what it is, Q's got to be at least this. This horrible expression, which actually works out that Q's got to be at least 3 over 2 delta plus 1 rounded up. And that's basically it. So we did one other thing in this, which is not quite the same flavour, but we looked at colouring bipartite graphs and whether we could improve Vigoda's, but this is really just looking for something that would work. So we use a different dynamics, which is the scan dynamics, where you just recolour the sides of the partition alternately, and we use this heat bath recolouring. That's we select an available colour at random from the set of available colours for each vertex. And you can translate this into rapid mixing for the Glauber dynamics. Notice that we can do all this independently because all we're looking at is the other side of the graph. So if you look at it, the bad thing that can happen is you choose a particular one of the available colours. That is the one that's different. So we define this matrix, which weights the thing down by 1 over the size of the available. That should be, yeah, it's the number. There's some A is both a set and a number here. So this is the distance. And if we use path coupling, just simple path coupling with this, it gives rapid mixing if Q is bigger than some function of delta. This function tends to 1.764 delta as delta tends to infinity. So this improves Vigoda's 11 delta over 6, which is about 1.834 delta. So for delta at least 14, it's at least as good. And if delta's bigger than 31, it's better. And this is all quite a weak result, and we didn't take it any further. And we could probably improve this by using some of the kind of optimization that you saw in the other two. But it just shows that this idea is worth thinking about still, and that coupling is not completely dead.
Are there any questions?
So nobody's going to leap to the defense of correlation decay, it seems.
Okay.